What is magnetic field strength? Magnetic field strength and magnetic flux density, they are pretty much proportional to each other. Magnetic field strength is basically whenever a current is flowing in a coil which has n number of turns, then it of course is going to produce a magnetic flux. So the way you calculate the strength or intensity of that magnetic flux is you take the product of number of turns times the current that is flowing in that coil and divided by the length of coil, and that gives you magnetic field strength H, and the unit of H is number of turns of coil, so turns times current, ampere, divided by length, meter, right? Ampere turns over meter. Always remember, anytime problems are given to you, always standard units are used until if it's been told that units are not standard in that equation. But always remember that centimeter is not a standard unit, meter is a standard unit. So anytime it is given to you that length is in centimeter, the first thing you're gonna do is to change it into meter. It's very important because again, otherwise your answer is going to be incorrect. So make sure anytime a problem is given to you in the quiz, exam, homework, and if the units are not in the SI unit, make sure to change them again, unless in the formula it is mentioned. When we are studying the formula, it is mentioned that the unit is not the standard unit. So far all the formulas, all the equations that we have addressed, all of them take standard SI units. So make sure to change them if they are not given to you in the exam, quiz, or homework. So as I mentioned, magnetic flux density and magnetic field strength, they are directly proportional to each other. So basically, the more current going to flow through the flux through the coil, the more flux is going to produce, and flux per unit area, magnetic flux density, is going to be greater until you have the saturation of flux, as we're gonna see pretty soon. Then the flux density is not going to increase. You can increase the current, but the flux density will not increase. That is, the flux will not increase, as we will see pretty soon. In any case, the flux density and the magnetic field strength are proportional to each other. Oh, by the way, in some of the problem, it will be asked to calculate the magnetomotive force. So we have electromotive force and we have magnetomotive force, which generally we call MMF, magnetomotive force. So what is MMF? MMF is basically this, N times I, right? The number of turns of the coil times the current that is flowing through the coil. That's magnetomotive force. That's the force that is required to produce the magnetism through a coil or in a coil. So in some of the problem, it may ask you calculate the magnetomotive force. Very simple, multiply the turns times the current. That's the magnetomotive force. All right, going back to this, magnetic flux density is proportional to the magnetic field strength, and the constant of proportionality is mu, which is permeability of the material. How permeable? What does permeability mean? How easy it is to magnetize a material. That's what the permeability means. Permeability of a material is calculated in general in terms of the relative permeability and mu naught, where mu naught is the permeability of the vacuum, which is taken as a standard, and mu r, which is the relative permeability of the material, is the permeability of a material with respect to the vacuum. Okay, so that's a number that can easily be found out through the tables for any material. What is mu r for copper? What is mu r for iron? What is mu r for plastic, glass, or anything? Number that you can find in tables or the characteristic or properties of that material. And mu naught is a standard value, which is 4 pi into 10 to the power negative 7 Henry per meter. So when you calculate B for vacuum, it is going to be mu, which will be mu naught for the vacuum, 4 pi into 10 to the power negative 7 times h, which will approximately be equal to h over 800,000. 1 over 4 pi into 10 to the power 7 is approximately 1 over 8. 4 pi into 10 to the power negative 7. 1 over approximately 4 pi into 10 to the power negative 7. Or 1 over 4 pi into 10 to the power negative 7 is approximately 800,000. So vacuum never magnetizes. No matter how much current is flowing through the vacuum, it will never magnetize. That's why it is always a linear relationship between the magnetic field strength and magnetic flux density through a vacuum, and through air as well. Air is also considered to have the same characteristic as vacuum. Now, if you have other materials, like you have some material that cannot be magnetized, like rubber, paper, which are called non-magnetic material, or you have some ferromagnetic material or magnetic materials that can partially or fully magnetize, you can create some curves like these, which are called BH curves, and then from these BH curves you can figure out that if your magnetic field strength has a specific value, what will be the magnetic flux density, and you from that relationship you can figure out what will be the value of a specific value of the permeability of that specific material at the time at the specific value of magnetic field strength and flux density. Observe that, of course, vacuum or air is linear relationship, it never magnetized. Observe iron starts when you're increasing the current through iron, increasing the magnetic flux density, then it starts linearly, but soon it starts saturating, and eventually it saturates. That is, no matter how much current you're gonna pass through iron, now there is no more magnetism. Once it reaches to a value of approximately 0.6 Tesla, then it is increasing very small amount, even though you're increasing the strength or current a lot. Why? Very simple reason, as we're going to study soon, because anytime you're creating an electromagnet, basically any electromagnet or any substance, it has dipoles, and if it is not magnetized, all the dipoles are in random direction, so there is no magnetism in that specific material. Once you start applying current or magnetic field strength to align those dipoles, then the dipoles start aligning in the direction of North Pole and South Pole, and as the alignment start increasing, it start becoming more magnetized. At one point, all those will be properly aligned in the direction of North Pole and South Pole, and at that time, no matter how much current you're going to increase beyond that time, since they are already aligned, they are they're not going to be aligned more, because alignment is already done. So after that time, basically your magnetism is not going to increase, no matter how much current you are going to produce. So we call that as a saturation point, and all the magnetic substance, they have some saturation point. All the non-magnetic substance, they don't really have saturation point, or under certain condition they can saturate, they can become magnetized, but generally, like rubber, you cannot get magnetized, it cannot get magnetized, maybe under some condition, but in general it won't. So we can use these BH curves to study the relationship between magnetic flux density and magnetic field strength, and we can also calculate permeability and stuff like that. And I believe, let's see, it's not responding, let's see.